Hi there, General Math students. So we were discussing shortest path analysis in the previous video. We're looking at something similar in this video. It's called minimum connection and involves Prim's algorithm, which I'll just show you here. Now, it's similar to the shortest path analysis, except rather than say you want to drive a car through a network to get from one end to the other in the shortest possible distance. With shortest path analysis, what we want to do is end up with a link between each of the vertices in the network, right? So if we look at this last one down here, we can see that each of the vertices in this network is linked by this red subgraph. So that is a subgraph of this network graph. It doesn't involve all the edges, but it involves enough edges to connect all the vertices somehow, and that in fact is the shortest way to connect them all. Okay, and it's things like if you were going to put up some power lines, for instance, or you had all dirt roads connecting towns, and you just wanted to make some sealed roads so that you could drive on a sealed road from one town to another, those sorts of things. Okay, so it's a bit different to shortest path analysis. Let's go through the example. Now, first off, we need to understand what a tree is. Now, we're not talking about a tree that grows in the forest or anything like that. We're talking about in networks, the definition of a tree. So a tree has no circuits. What's a network? A connected graph with no circuits, loops, or parallel edges. So here in this first one, we could do a circuit through here. So it's not a tree. This graph here has a loop, not a tree. Here we've got parallel edges that also make a circuit, not a tree. This one, no loops, parallel circuits, or parallel edges or circuits, but it's not connected, so it's not a tree. This is the only one that's a tree, this last one. It's connected, and there are no parallel edges, no loops, no circuits. So that is a tree. Now if we look at these, a spanning tree is like when you put part of the total network, you can draw it in on top of the original network, like this one here. Now you notice that we've got this blue network. We'll just look over here, this blue network. Now if we make these edges red, that makes a subgraph of this network. So it's not all of the edges are involved, only some of them, and it's a tree. That red network the red edges make a tree because there are no circuits or loops or parallel edges, only with the red parts. If we look back at this one here, you could do a circuit through there, but this edge here isn't included in that subgraph, that red subgraph, so no circuits, right? So it's all about making a tree like this in the network. Can you think of some other trees that could exist in this network? We've got a couple here. Maybe you want to pause the video and then I'll show you a couple of others that occur to me. Okay, so see if you found a few more. I can see this one here. You could do this. Yeah, that's a bit different. So all the all the vertices are connected somehow now by that subgraph. What else have we got? So we had that one. We could do something like this, I suppose. That one there is another one, and you might have found some other ones. So let me know if you do. Anyway, let's get on to Prim's algorithm. We have a zoo here which needs to be upgraded. Okay, and they want to have they've got all gravel paths. They want to resurface some of them with concrete so that you can walk through each animal exhibit between them along asphalt paths. but we won't be resurfacing all the paths, only the ones that would make it possible to walk along asphalt paths from one exhibit to another and do it in the shortest length possible. So we're going to start, we'll look through this example and then we'll do a bit at the end where we redo it from a different place, but the step one in Prim's algorithm is to choose any vertex, okay? And here they've chosen vertex C, right? So they choose C, so we'll just go with that. So we choose vertex C. Now, the idea is to include edges, and that means we connect to more vertices as we go, but we want to pick the lowest number edge and we've started at C, so we have to pick something that's touching C, and there's only two options, the 38 or the 28. So we go with 28. So now we've got C and that 28 edge and D involved. So when we move on to the next bit, we need to choose, okay, what's the next lowest number involved that's connected to C and D? And it could be 38, 49, could be 30, oh not 35, not that one, sorry, but 20 or 26. So that's why they've chosen 20, because that's the lowest of those numbers. And so now we're going to look and see, okay, we've got C, D and E involved. What is the next lowest number that we could connect to that? And remember, each time, because the network's going to get bigger, you can't make any loops or parallel edges or circuits. So I'm looking here and we've got a 26, a 29, 32, 35, 49 are all touching E, D or C. So the lowest of those is 26. If we include that, does it make a circuit? No, it doesn't seem to. So if we look to the next page, you can see that they've included that 26. So now it's about saying, okay, we could include this 65, the 29, 32, 35, 49 or 38. Any of those are up. The lowest one, the lowest one on offer is of course the 29. So why don't we include that? They've included 32 next. Well, that would make a circuit there. So that's not allowed. 29 cannot be included because it would make a circuit. Remember, we need to make a tree through the network. So we go for the next one up that doesn't make a circuit or a loop, and that is this 32, which connects A. Now we've only got one vertex by this stage that's not connected to the tree, and that's B. So once we get to this point, it's really about saying, okay, how do we connect B? Via 38 or 27? Well, we're going to choose 27 because it's the lower of the two and it doesn't make a circuit or any of that stuff. So we end up with that as our spanning tree, and we could resurface all those red edges with asphalt, and that would be the shortest way to do it, 133 metres. Now, it doesn't matter where we start, and just to prove that, I'm going to do it again, but I'm going to start at vertex A and go through the same process. So vertex A, 27, 32 or 65 are my only options. I'll go with that one first. Now I can choose 38, 49, 35, 32 or 65. The lowest one is 32. Okay, you might want to pause the video now and continue on from there, connecting edges and vertices, the lowest one that's touching your current tree. And as long as you don't make any loops or circuits, then you keep going with the lowest number until you get all the vertices as part of the tree. So have a go at that, then I'll try it. Righto, so we've got this so far. So the next lowest one would be the 20, and then the 26, and finally the 28. So you can see that we end up with exactly the same spanning tree as when we started with C first. So it doesn't matter where you start, choose any vertex and you should end up with the same spanning tree. Okay guys, so go ahead now and try some of the questions in the description for the video.